Hello again, welcome back to this video channel with practice problems for professional actuarial examinations. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. The video channel where I show practice problems for professional actuarial exams is at smarturl.it/pass actuarial exams. I direct the actuarial program at Illinois State University. You can find information about the program at smarturl.it/actuary. If you would like to make a tax-deductible donation to support our students, please go to smarturl.it/help ISU actuary. Here's a problem for today. A random variable x has the cumulative distribution function, which is 0 for x less than 1. It's x squared minus 2x plus 2 over 2, the whole quantity divided by 2, for x between 1 and 2. And then it's 1 for x greater than or equal to 2. Calculate the variance of x. Well, to understand what's going on in this problem, it is crucial to realize that this is a mixed distribution with a point mass at 1 for x equal to 1. This can be seen by analyzing the limit of this cumulative distribution function, CDF, at 1 from the left equal to 0, and the right-hand side limit of CDF at 1, which is equal to 0.5. Or better yet, just drawing the graph of the CDF. And that's the graph. So you can see that it's a flat line of 0 between 0 and 1. Then it's this upward sloping curve between 1 and 2, but it jumps at x equal to 1. The CDF jumps from the value of 0 at 1, and then it suddenly becomes 1/2. And of course, there is no value at 0 at 1. It's just the left-hand side limit as the CDF, as x approaches 1, the CDF approaches 0 from the left-hand side. But from the right-hand side, it approaches 1, and it is actually equal to 1 also. I'm sorry, it approaches 1/2, and it's equal to 1/2 at 1. So the function is continuous from the right, which, of course, a CDF needs to be by definition, basically. But it's discontinuous at x equal to 1 because of the left-hand side limit not being equal to the right-hand side limit and the value of the function. Then at 2, the function is continuous. It may look like there's a little bit of space there, but it's not. It's intended to be connected, so I apologize about the imperfection of the graph. So it's continuous there, and it reaches the value of 1, the maximum value of a CDF. For x equal to 2, the CDF reaches the value of 1. And maybe I should apologize, I say CDF all the time. I'm assuming you're used to this. This is the American way of speaking. You always use acronyms in the US. If you're an international student, you will need to get used to this. And, you know, anytime somebody throws these acronyms at you, just stay calm. And somebody says CDF, you just say, what does this CDF mean? And let's see what happens. But you have a right to ask what people mean. I'm from Poland originally, and we don't use acronyms. Well, only during the communist occupation, the communists use acronyms. But not always, because in Russian, of course, they don't use acronyms. They just take the first syllable of every word and create a new word, like komsomol used to be a word created out of three words. And in German, of course, you wouldn't just say CDF. You would take all 3 words and make it into one word. So you would say cumulative distribution function, 1 word, right? Or the German word for ambulance. Ambulance is ambulance in every language. Even in Polish, you can use that word for ambulance. but in German it's Krankenwagen. And what is actuarial science? It's Versicherungsmathematik. So anyway. So for a continuous distribution, the graph of its CDF is continuous non-decreasing function. But we have a jump here, we have this discontinuity, so this is not a continuous distribution. For a discrete distribution, the graph of its CDF consists of a series of horizontal lines with jumps between them. If you see both jumps and pieces of continuous increasing curves, you're looking at a CDF of a mixed distribution. The jumps are at the points where the discrete portion has positive probability function, and the sum of the jumps is the weight assigned to the discrete part of the mixed distribution. In this problem, there's only one jump at 1. This means that the discrete portion of the mixed distribution is degenerate at 1. Degenerate probability distribution is the one that concentrates all probability at one point. The weight of the discrete portion is the size of the only jump. It's 1/2. Given that, we can see that the distribution in this problem is a mixture of a degenerate distribution concentrated at 1 and a continuous distribution spread out between 1 and 2. And we decompose the CDF into a weighted average of the CDFs of those two, and the weighted average with the weights that we just identified. The discrete part has the weight which is the sum of the jumps, and the continuous part has the weight that is 1 minus that sum. Well, in this decomposition, the first CDF, the f sub x1 of x, is 0 for x less than 1 and 1 for x greater than or equal to 1, because we know that that's where the jump is. So this is the formula for the CDF of a degenerate distribution concentrated at 1. The formula of f sub x2 is found from the fact that we know that f sub x of x has to be equal to this weighted average. And we just solve it for s sub x2 of x, and it's got to be equal to 2 times f sub x of x minus 1/2 f sub x1 of x, based on what we know. So it's 2 times f sub x of x minus f sub x1 of x. And you just calculate it, and it comes out to be 0 for x less than 1, x squared minus 2x plus 1, which is x minus 1 squared for x between 1 and 2, and 1 for x greater than or equal to 2. Now note that the graphs of f sub x1 and f sub x2 are as follows. The first one is the discrete part, and the second one is the continuous part. That curve between 1 and 2 and the second part, that's actually a parabola from a quadratic function that we identified there. If you take half of the first graph plus half of the second graph, we get the graph of f sub x of x. Just imagine, multiply the first thing by 1/2, so you just move the straight line at 1 to 1/2, and then multiply the other one by 1/2, so you would just kind of squeeze it down to 1/2 level, add them up, and you're going to get exactly this graph at the bottom that you see here. And we also have f sub x1 of x, the probability function for the first distribution, to be 1 when x is 1 and 0 otherwise, and the second one is a continuous distribution with a density of 2x minus 2 for x between 1 and 2 and 0 otherwise. And of course we immediately see that e of x1 is the same as e of x1 squared, and it's 1, and e of x2 is the integral from 1 to 2 of x times 2x minus 2, and that comes out to be 2/3 x cubed minus x squared evaluated from 1 to 2. So it's 4/3 minus negative 1/3, so it's 5/3. And e of x2 squared is the integral from 1 to 2 of x squared times 2x minus 2, so it's 2/4 x to the 4th minus 2/3 x cubed evaluated from 1 to 2, and that's 8/3 minus negative 1/6, so 17/6, 17/6. And finally, the variance of x is e of x squared minus e of the mean of x squared. And For a mixed distribution, where the CDF is a weighted average of two CDFs, the first moment, second moment, third moment, and so on, every moment is a weighted average, the same weighted average of the moments of the pieces that are combined in the mixed distribution. So it's 1/2 e of x1 squared plus 1/2 e of x2 squared for e of x squared. And the first moment is 1/2 e of x1 plus 1/2 e of x2. We just calculated all those, so we plug them in, and we get 23 over 12 minus 4/3 squared, so it's 5 over 36. This is answer C. Now, the above is actually a standard procedure for finding the variance of a mixed distribution. The moments are found as weighted averages of the moments of its components, and then the variance is the difference between the second moment and the square of the first moment. You cannot, however, find the variance as a weighted average of the variances of the pieces of a mixed distribution, and that is why real exam questions on this topic are usually about the variance. This allows the examiners to eliminate candidates who did not study mixed distributions. And, well, what is the true purpose of actuarial exams? You need to keep it in mind. The true purpose of actuarial exams is, of course, the same as the boot camp in the military. The purpose is to get rid of you. And your purpose is to not give them the satisfaction. And if you want to just study just enough to pass, just to pass, you don't want to work too hard, or you don't want to memorize, it's too much, it's all this work, why do I? Well, then you don't want to be an actuary, because you're the one that they want to eliminate. The proper way to study for actuarial exams is to overstudy. What kind of actuary do you want to be? The one who doesn't pay any attention to details? And you just, make a slight mistake, lose $5 billion, no biggie, right? You'll just replace it, of course. Or, as I like to say, would you like the surgeon who's going to do the surgery on your child to study just enough to pass? Or would you rather have that surgeon study everything in an extreme detail? Well, I would urge you to study everything in extreme detail. Please, please study everything in extreme detail. It's also worth noting that this problem could have been solved with the use of the Darth Vader rule. But the above longer solution is important for you to know and understand. How does Darth Vader do it? Well, we note that x, the random variable we're studying, is non-negative with probability 1, non-negative almost surely. So Darth Vader rule applies, and the expected value must be equal to the area indicated in the graph. This is the graph of the CDF, not of the survival function. The survival function is 1 minus the CDF, so if you want to draw that graph, you would just need to calculate 1 minus what you see here. But the area under the graph of the CDF, between the line where the horizontal line at the level of 1, where you reach the value of 1 for the CDF, and the area under that line and above the graph of the CDF, that's the same as the integral of the survival function, because this is the integral of 1 minus f sub x of x, which is the survival function. So this area is the expected value of this function. And the area indicated can be calculated as 1 between 0 and 1 plus the area between 1 and 2, which is calculated as the integral from 1 to 2 of 1 minus x squared minus 2x plus 2 over 2. So it's the integral from 1 to 2 of x minus 1/2 x squared dx, which is 1/2 x squared minus 1/6 x cubed evaluated from 1 to 2. That's 2 minus 8 over 6 minus 1/2 minus 1/6, and it comes out to be 1/3. So if you add it to 1, you get 4/3, and that's the same value as we have obtained above for the expected value. The question is about the variance, so we're not done yet here. And now we use the version of the Darth Vader rule for the second moment. E of x squared is 2 times the integral from 0 to plus infinity of x times the survival function. And that's 2 times the integral from 0 to 1 of x times 1, plus 2 times the integral from 1 to 2 of x times 1 minus x squared minus 2x plus 2, the whole quantity, over 2. Well, that's 2 times 1/2 plus, well, the integral of x is x squared, and yes, 1/2 x squared. So sorry, 1/2 x squared, and the value weighted from 0 to 1 is 1/2. That's where this 1/2 comes from. Plus 2 times this integral of the second function, and 2 times 1/2 is 1, plus the integral from 1 to 2 of, if you multiply it out, is minus x cubed plus 2x squared. And the integral of that is minus 1/4 x to the 4th plus 2/3 x cubed, evaluated from 1 to 2, will give us minus 1/4 times 2 to the 4th plus 2/3 times 2 cubed, and we subtract the value at 1, which is negative 1/4 plus 2/3, and if you do all the calculations, that's 23/12. This is the same value of the second moment as we obtained before, resulting in the same answer choice, the same value of the variance. So we get the same result. It's very important that you learn about mixed distributions. Insurance contracts modify the distributions of the losses in a way that regularly produces mixed distributions. That's why you need to know them, because they actually matter for practical work. And it's a good way to throw a confusing question into the exam and, well, to do what the exams are for, and that's to get rid of you. But your job is to not give them the satisfaction. Please remember, this is copyrighted material. The problem itself comes from Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.